All right, so we're here today to do a practice FRQ. This FRQ is off of the 2016 AP Physics 1 exam. So if any of you are out here trolling me, trying to catch me doing something wrong, this is a released question, so College Board need not be worried. Both the question and the rubric has been released. And AP Trevor and I go way back, although he will not reply to any of my tweets. So what we're looking at here is, if I zoom in this picture, it's kind of weird. It is a hanging oscillator, meaning instead of having a horizontal string, this string is hanging vertically. And when it's set into motion, we can see that when it's at rest, it's on the left here. And on the right, we got some kind of weird stuff going on where we have this this wavelength, or this standing wave, a nice and big wavelength here, a smaller wavelength here, and yet an even smaller wavelength there. So kind of some weird stuff going on. And that's why AP is so good at what they do. They make the most random crap and ask you to explain it. And if you know what you're talking about, it's kind of easy. But if you don't, it's not. So this problem, again, kind of breaks it down nicely for us. It says, first off, the tension at point P is greater than the tension at point Q. All right, so the very first thing you want to say is not that the tensions are the same, right? AP will never guide you or steer you in the wrong direction. It will never say something and then have you contradict it. So it says the tension at point P is greater than the tension at point Q. The whole point of part A is to get you thinking about what's going on and to set you up for success. So P is higher up than Q here. And the question is, why is the tension at P higher than Q? This has nothing to do with simple harmonic motion. This has to do, actually, kind of stuff we talked about way back with forces. And if I go back to the question, it says the figure above shows a uniformly thick rope. If something's thick, in AP's mind, thick does not equal, that was a bad not equal, massless. So a thick rope versus a quote-unquote, we have a thin rope, would equal massless. A thick rope, therefore, is not massless, which means that point P is supporting all of that weight below it. Point Q is just supporting the weight below it. So technically, there is more rope that point P is supporting. So therefore, that and we know back from Unit 2 is that if there's more rope, there's going to be more mass, so the weight has to be equaled out by the tension. So more mass, more weight, more tension. And if you put something that says something like that, well, according to the rubric, you get 1 point for saying that there's something to do with there's more rope below point P, and you get 1 point for saying something about that the tension counteracts the weight. So those are the 2 points that you need to get for the first part. Now, the second part is the actual simple harmonic motion of that. So let's go forth to that. So a student hypothesizes that increasing the tension in a rope increases the speed at which waves travel. In a clear, coherent paragraph-length response, explain why the standing wave shown above supports the student's hypothesis. Okay. If you're like me and you're really good at memorizing equations, you might have remembered something that we did a couple of times this unit, and you might instantaneously jump to velocity in the string equals the square root of the tension in the string divided by the linear mass density, where the linear mass density is mass per unit length. And you're not wrong, okay? That is 100% correct. That formula, it's something we talked about multiple times. That formula is not wrong, okay? Here's the thing, though. Let's say I wanted to write a paragraph about that formula. I would get no points for that. And here's why. The formula, although being good and being true, has nothing to do with this picture right here. So this picture is supposed to be our evidence that validates this formula. Okay. Now you don't have to know this formula to do this question or to write this paragraph, but it sure helps because we know that it's correct. So although we know this beautiful formula about the velocity of the string equaling the square root of the tension over the linear mass density, we're going to go ahead and ignore the fact that we know it because it doesn't actually prove this. It doesn't prove that what is happening here correlates with that formula. So instead, we got to take a different approach. And let's think about what's going on in this picture. Well, what are some things that I actually get from the picture? I already mentioned one of them, right? Let me blow this up. Just let me turn. No, I'm not going to do that. I'd like to invert it, but well, hold on. Please hold. All right, so we'll just go from right here. So a couple of things. We can get one thing from the picture right away. And we know that this place at point P, we already talked about this. Here's our wavelength for point P, and then here's our wavelength at point Q. And what do we notice? We notice that the wavelength of P is much larger than the wavelength of Q. So we can see that first and foremost, the wavelength at the top is larger than the wavelength at the bottom. And some of you are like, yeah, well, so what? Okay, well, my so what answer deals with this concept of the fundamental wave equation, and that is that velocity equals frequency times wavelength. So I got some stuff with wavelength. I'm wondering about stuff with the speed of the wave, so I'm curious about this guy. So my next question is I know stuff about this, I'm looking about stuff about this. What about frequency? So the point is, though, if this is all set up to the same oscillator, then the frequency has to be the same throughout the entire string. So the bottom of the string can't be oscillating faster or slower than the top of the string. They have to have the same frequency because it's set up to the same harmonic oscillator. So what we see that with this fundamental relationship is that the frequency is the same throughout. The wavelength is larger at the top than it is at the bottom. Well, from part A, if you recall from part A, we already determined that tension is greater at the top. Okay, so tension's greater at the top, then therefore, if it's greater at the top, then the wavelength is greater at the top, and from our fundamental equation, the higher the wavelength, according to this then, we must have a higher velocity. So, and that higher wavelength corresponds as well to a higher tension. So, that might have gotten a little confusing, but a greater tension at the top of the rope, point P has a greater tension at the top of the rope. That greater tension is causing a greater wavelength. The greater wavelength means that it has to have a greater velocity because the frequency is the same compared to part Q. So greater tension, greater wavelength, therefore a greater velocity. And if you think about that, that also makes sense because if the velocity is greater, the wave can travel a greater distance in one cycle. And that directly corresponds to the wavelength. So if the wave is traveling faster, it's going to go a greater distance in the same amount of time. So greater velocity, greater wavelength. So you need to somehow take all that and put that into a paragraph. And I'll talk you through an example paragraph. I would say, you could say something like the wavelength at point P is greater than the wavelength at point Q. Since velocity equals frequency times wavelength, and the frequency has to be constant throughout the rope, the velocity at point P must therefore be greater than at point Q, since point Q and P have to have the same frequency. I might have said that twice. From part A, we also said that the tension is greater at point P than at point Q, so therefore the tension must directly correspond to the velocity of the wave. So we'll stick with that. I talked through that between both slides in probably about 10 minutes. And again, I didn't even stay on task. This was a 13 or 12 or 13 minute problem that you should have had. So not bad in terms of a paragraph length response, not bad. Again, it helped you set up by asking you a question in part A, and then you finish it out with a paragraph in part B. So total of 5 points for part B, and I'll point them out. Well, that's a point. That's a point. Frequency has to be the same. Using the fundamental equation, that's a point. And then point 3, something from part A, tension is greater at the top. And you might say, well, that's only 4 points. Well, guess what? There's the pity point as well. So we'll call that the pity point. For a response that has sufficient paragraph structure as described in the published requirements for the paragraph length response. That is the pity point. Did you try to write a paragraph that answered the question without saying anything wrong or just kind of digressed? Unlike me, boom, 1 pity point. So that is the breakdown of that question. Now, before I let you go, I want to point out one other thing. And this is where we get such a bad rap. All right. This question, how'd you do, right? When you thought about it, how'd you do? All right, so this is a 7-point question. So my question to you is, how hard was it to get all 7 points? And it really wasn't that bad, right? Well, guess what? The global average of everybody who took this test and got this question, 2.2 out of 7. So if you got at least 3 points, which means that you got the first part right and tried to write a paragraph, even if you didn't get the paragraph right, you tried to write a paragraph, you just got a 3 out of 7, okay? So yes, I've said that this is a difficult exam. It has traditionally it's tough, right? You can do this. You can do this exam. It's not that bad. If you take an approach, you try to solve the problem, you're going to be all right. Think about what you know, think about what you've learned, and you got to bring it together, because a 3 out of 7 is a 42%. If you can get, a 4 out of 7, you just passed the AP exam. So just think about it that way. It's doable. It's manageable. Good luck. We got one more unit to cover after this, and that is electrostatics and DC circuits.